Jarosław Grytczuk, who will speak about twins and permutations.
Thank you very much. So this will be a work of me and my two colleagues, Andrzej Dudek and Andrzej Ruciński. And mostly I will present open problems with some results. And first, let me start with the definition of similarity of permutations that you probably know very well. So first of all, for me, a permutation is just a sequence of distinct integers. And I like to think of such sequences in the following pictorial form. So we may have two different sequences that can be similar in the quite natural sense. When we enumerate the terms of the sequence according to the size, we will see some real permutation of length equal to the length of such sequence. And if for two such sequences we get the same permutations, we say that these two permutations are similar. Okay, so two permutations are similar if they have the same relative order. And well, I start with the most general notion of twins in permutations. So these are just two subsequences that are disjoint and similar in a given permutation. Okay, so a pair of twins is a pair of two disjoint subsequences that are similar in the previous sense. And the length of twins is the length of one of them. So for instance, here on this picture, we see two twins of length 3. And by T of pi, I denote the maximum length of twins in a permutation pi. And of course, so for instance, in this example, this is not 3, this is equal to 4, because we can find actually longer twins. And here is an example. And the natural questions we are studying is how long twins are contained in every permutation. So this can be formalized as a function, kind of extremal function. So we look for the minimum value of T of pi over all permutations of a fixed length n. And we can also define it equivalently as the largest case, such that every permutation of length n contains twins of length k. And what do we know about this function? So first easy observation is that every permutation of length n contains twins of size square root of n, roughly. And this follows from the quite famous and quite fundamental result by Erdős and Szekeres, which just says that every permutation of that length contains monotone subsequence of size square root of n. And it is clear that a monotone subsequence split it in any way into two equal subsequences, I mean two subsequences of the same length, gives a pair of twins. So this is the starting point. And here is another observation made by Gavron, who proved that this function is also bounded from above by a kind of this exponential expression, so n to 2/3. And he proved this result by a probabilistic argument, which actually also gives that almost every permutation satisfies this bound. So so there exist permutations with twins no longer than n to 2/3, and almost every permutation has this property. And he conjectured that actually this function is Okay, so this is the conjecture, and maybe the most intriguing in the whole talk. Then I just presented two results, and well, you may skip the former result. The next one says that this conjecture is true for random permutations, for almost all permutations, if you prefer. And the deterministic result was also improved by the same two authors to 3/5. And that's all we know about it. And since we are not able to solve this conjecture, we are thinking of some variations. And the first variation is tight twins. So these are twins that occupy a segment. So they are placed in a permutation in this specific way. And we define similarly the extremal function. And now we could bound this function from above by a constant. So the proof is also probabilistic, and it says that we can build, or just there exist, long permutations such that any window or any segment of length more than 24 cannot be splitted into two similar permutations of the same length. So I think that's quite nice result, and I believe, or I would like to believe, that the lower bound for this function is the true value of it. And the related problem of enumerative flavor is to look for the number of such permutations of length 2n that can be decomposed into two similar subpermutations. Okay, and still a more restrictive version of twins is tight twins, such that each of the parts also occupies a segment, which we called block tight, but they can be also called squares. Okay, so the similarly defined function can be considered for such notion, and here we have best possible result by these four authors who proved that actually this function is equal to 1, which means that we can construct permutations without squares of length more than 1. Of course, 1 is unavoidable because two elements are similar. And clearly this result resembles what was inspired probably by the famous result of Thue, and therefore we can think about generalizing these results in this direction, that we can take any pattern which is avoidable on words, and we try to find permutations avoiding such patterns in the sense that all occurrences of pattern has blocks of bounded length. I think this conjecture is quite plausible, maybe even not very hard to prove. And another variation is in a different direction. We look for a weaker notion of twins, weaker type of similarity, where we just look at the shape of a permutation. So we call a shape of a permutation a binary sequence that reflects just the relation between consecutive elements, whether it is bigger or smaller. And again, a natural definition which says when two permutations are weakly similar, they have the same shape, and the same questions can be repeated for such a weaker notion. And we have now better bounds for this function. It looks like it is. So first of all, it is linear in n, and maybe it is even equal to asymptotically to n half, which would mean that we can, from every permutation, we can remove a small part and in this way we get a pair weakly similar twins. Yeah, so this is the conjecture I just commented on, and the same enumerative problem can be stated also for this weaker version of twins. And well, now I just quickly show you something about twins in other structures. So for instance, in words, you can look for twins in this sense, and actually, so there is a very nice result which says that in every binary word you can find a very long pair of twins. Again, the same, maybe similar to the previous conjecture, and actually this result was the largest inspiration for us to study these twins in permutations. But you can also study twins in graphs. There are quite nice results. For instance, the similar function. So in a graph, you can define twins in maybe diverse ways, but the most natural is that this is a pair of edge disjoint subgraphs that are isomorphic. And with such notion, an exact asymptotics of the size of such twins was discovered. For trees, we have something closer to this half of the size of the tree, which is similar to, in some sense, similar to the result for words. And well, you can try to study this problem in quite arbitrary combinatorial structures. So for digraphs and for hypergraph, there are some results, but for pulses, matrices, or other, I don't know too much. And some quite nice problems you can find in edge-ordered graphs, which is closer to the topic of permutations. So for instance, we are given a graph, we have some labeling of its edges, enumeration of edges, and we can look for twin paths, which are paths, simple paths, such that the first half is similar to the second half in the sense of similarity of permutations. And we can define the largest K such that every edge ordering of a graph has such a twin path. And for instance, it is even not known. So maybe I should say that this topic is not studied at all so far. So everything here is quite open. So for instance, even for cliques, it is not known whether we can find a pair of such twins of length almost n. But something was proved for a problem that was also an inspiration here for just monotone paths, which means paths with monotone sequence of these labels. And it is also conjectured here that this should be linear in n, and this is almost proved now. But I believe that for twins defined like that, it should be larger, of course. And for instance, for planar graphs, we can try to bound the length of such twin paths. Maybe it is true that we can bound it by some constant. Okay, I'm looking for time. Still have maybe some minutes. Well, so I was very quick. So this is the last problem I would like to present. So I call it the problem of Ulam because he asked similar question, at least for graphs, but I think his motivation was connected to maybe even some things like Banach-Tarski paradox. So it's about the compositions of structures into pairwise isomorphic structures. Okay, so in our setting of permutations, this looks also quite natural. So when we are given two permutations, we can ask into how many subsequences can we split this permutation such that these subsequences can be matched into pairs, and these elements of pairs are similar. So every pair of permutations has such number. Of course, if one permutation is increasing and another is decreasing, then of course this number will be equal to the length of the permutation. But we would like to know what happens on the average, say. So when we pick a random pair of permutations, what is the expected value of such number? Okay, I think it's maybe that's it. Thank you.
Oh, thank you, Jarek. Does anyone have any questions?
We really have time for it, no problem.
Yeah.
I should stop maybe sharing this.
Or maybe somebody will ask something.
I don't know how to stop sharing.
Somewhere at the top, there must be a menu. Yes, Stepan.
Well, do you have any brute force search results for small numbers?
Well, we were making some experiments. Mainly, one of these co-authors, Andrzej Dudek, was programming computer to find some properties of short permutations, and it was mainly by brute force. And I don't remember now any details, but you can find it in papers. We have 4 papers on this topic, and all of them are on archive. If you want, I can send something.
Thank you.